Time dilation is an interesting consequence of Einstein's theory of relativity and plays a critical role in the operation of global positioning system satellites. These satellites orbit the Earth at high speeds and at different altitudes relative to the planet's surface. According to the general theory of relativity, time flows slower in stronger gravitational fields, which means that clocks on the Earth's surface tick a little slower than in space. The special theory of relativity predicts that due to the high velocities of satellites, time on board them also flows slightly slower than that of a stationary observer on Earth. For the global positioning system to work accurately, the clocks on the satellites must be precisely synchronized with the clocks on Earth. Without correction for time dilation, even a tiny discrepancy can lead to significant errors in position calculations. Specifically, the combined effect of special and general relativity means that the clocks on the satellites tick faster than on Earth by about 38 microseconds per day. While this may seem insignificant, over time it will lead to significant errors in position measurements, with errors as large as 10 kilometers per day. To counteract this, the clocks on the global positioning system satellites are set to tick slightly slower before launch, so that they match the pace of Earth's clocks when they reach orbit. In addition, onboard computers constantly adjust satellite time to account for relative motion and gravitational differences. Ensuring this level of accuracy is critical for the myriad applications that depend on a global positioning system, from navigation and mapping to synchronizing telecommunications and even assisting in financial transactions. Thus, correcting for time dilation embodies an elegant interplay between theoretical physics and practical technology, emphasizing that our understanding of the cosmos directly affects everyday life. Gravitational waves are ripples in the very fabric of space-time, caused by some of the most violent and energetic processes in the universe. Predicted by Albert Einstein's general theory of relativity, these waves propagate at the speed of light and are generated when massive objects accelerate, especially in scenarios with extreme gravitational fields. Examples include merging black holes or neutron stars, supernova explosions, and even the rapid rotation of massive stars. Detecting these complex waves requires very sensitive equipment because they can be stretched and constrained. The best-known instrument for this work is the Laser Interferometer, Gravitational Wave Observatory's laser interferometer called LIGO. LIGO consists of two L-shaped interferometers, one in Washington State and one in Louisiana, each 1 kilometer long. A laser beam is split and directed at each shoulder. If the barrier wave passes through, the length of the arms will change slightly, which will change when the laser beams return and recombine. When the beams return and recombine, even if they are of different lengths, they create an interference pattern that can be measured with certainty. In 2015, LIGO directly observed cosmic waves from colliding black holes for the first time. This discovery confirmed one of the key predictions of the general theory of relativity and opened up a new way of looking at life. This event marks the beginning of Earth wave astronomy. As technology advances and new observatories like Virgo in Italy and the future Kagra in Japan become available, we will be better able to find the sources of these cosmic waves. By studying waveguides, scientists aim to uncover information about objects and events that were previously hidden from our view, allowing us to gain a deeper understanding of the dynamics of the world. Wormholes, imaginary units of space-time, have long captured the imagination with their ability to travel faster than light. By solving the equations of Einstein's general theory of relativity, wormholes can provide the shortest path between distant places in the universe. Imagine a tunnel whose two ends are at different points in time and space. If such a hole exists, traveling through it would allow humans to travel great distances instantly, bypassing the moon's speed limitations. However, there are several major problems with using wormholes to travel at speeds faster than light. The first reason is stability. Most wormhole remedies are said to collapse almost immediately after formation, so nothing happens even in the light. In order for the wormhole to stay open and be able to travel, it would need some kind of alien material with negative energy density. Such objects prevent wormhole shrinkage, but creating and maintaining these strange materials is beyond our current technological and scientific capabilities. Even if we were able to stabilize a wormhole, there are questions about its passability and safety. Intense gravitational forces near the throat of a wormhole can stretch and compress anything that tries to pass through it, a process often referred to as spaghettification. In addition, wormhole solutions sometimes involve the existence of causality paradoxes, such as the possibility of time travel, which entails many theoretical and practical complications. Although wormholes remain a fascinating idea in theoretical physics and a staple of science fiction, actual evidence of their existence or the ability to use them for travel remains elusive. At the moment, they provide a rich field for thought experiments and highlight the deep complexities of space-time. But they are far from a practical solution to the problem of traveling faster than light. But the study of wormholes continues to push the boundaries of our knowledge, forcing scientists to think beyond known physics. Frame stretching, also known as the Turing focus effect, is a surprising phenomenon that occurs near large rotating objects. According to Einstein's general theory of relativity, mass and energy can warp space-time, creating the wave effects we see. But when something changes, it doesn't just warp space-time, it pulls it together. Think of space-time as turbulent and rotating matter, such as a star or black hole that can be induced. When an object rotates, it warps space-time. This effect is more pronounced near massive and rapidly rotating objects, such as neutron stars and black holes. The closer you are to these objects, the stronger the frame dragging effect. It is very difficult to discern the frame, because the effects are imperceptible and require sensitive equipment. One of the best confirmations of this phenomenon came from NASA's Gravity Probe B mission. Launched in 2004, the spacecraft carried ultra-precise gyroscopes designed to measure tiny changes in angles caused by Earth's rotation and the tightening of space-time around it. After years of analyzing the data, results have been obtained that confirm the presence of the frame dragging effect, albeit on very small scales. Frame dragging has significant implications for our understanding of the cosmos. For example, around spinning black holes, this effect can affect the trajectories of particles and light, shaping the structure and dynamics of the accretion disks and jets emitted by these mysterious objects. By studying the tug-of-war, scientists are not only testing and refining our understanding of the general theory of relativity, but also gaining crucial insights into the Earth's complex behavior near some of the most extreme conditions in the universe. The twin paradox is a thought experiment that clearly illustrates the definition of time, the theory behind Einstein's special theory of relativity. In this case study, consider two identical twins. One of them stays on the ground, while the other moves through space at close to the speed of light. According to the special theory of relativity, twins traveling at higher speeds will live less time than the person behind them. Here's how the paradox is presented. A traveling twin travels to a distant star at close to the speed of light and then returns to Earth. Upon reuniting with the Earthbound twin, the traveling twin finds that less time has passed for him or her than for his or her sibling remaining on Earth. While the Earthbound twin may age by, say, 10 years, the traveling twin may age by only a fraction of that time, depending on the exact speed and duration of the journey. This discrepancy arises because, according to the special theory of relativity, Moving clocks go slower when observed from a stationary frame of reference. The term paradox came about because it initially seems illogical. We might think, if each twin thinks the other is traveling, why not use the same definition of time? The answer is that the traveling twins experience acceleration and deceleration while traveling, breaking the symmetry of the situation. The reference frame of the traveling trap is 0, 0, 0, unlike the neutral reference frame of the home trap. The twin paradox describes the real and measurable effects of the relationship. In fact, this effect is not just a curiosity. This has practical applications, such as in the Global Positioning System satellites, where time dilation must be accounted for to maintain the accuracy of navigation signals. Thus, the twin paradox provides a glimpse into the strange and illogical nature of time in our relativistic universe. The mysterious gamma-ray glow at the center of our galaxy, often called the galactic center of GovXS, has puzzled astronomers since its discovery. High-energy gamma rays detected by telescopes such as the Fermi Gamma Ray Space Telescope seem to emanate from a region densely filled with stars, dust, and energetic phenomena. The exact source of this gamma radiation is still under investigation, and several convincing theories have already been proposed. One of the main hypotheses suggests that dark matter particles can annihilate each other in the dense region of the galactic center. Unfortunately, most of a planet's mass is invisible except through cosmic influence. If dark particles collide and sometimes disappear, they can emit very powerful gamma rays as a result. This is a revolutionary discovery that sheds light on the nature of darkness. According to another theory, the intensity of gamma rays is related to the number of millisecond pulses. These are rapidly rotating neutron stars that emit beams of radiation, including gamma rays. They are thought to be abundant in the crowded central regions of our galaxy. If these millisecond pulsars are indeed the source, it will mean that our ideas about stellar population and high-energy processes in the inner galactic nucleus need significant adjustments. Wow! Alternatively, the glow of gamma rays may be the result of cosmic rays interacting with dense gas clouds at the galactic center. Cosmic rays, high-energy particles traveling through space, can collide with gas atoms, producing gamma rays. Given the complex environment in the galactic center with its intense magnetic fields and high stellar activity, such interactions could well have produced the observed excess of gamma rays. While scientists continue to explore these possibilities, each potential explanation offers a fascinating glimpse into the dynamic and energetic processes at the core of our galaxy. Understanding the true source of gamma rays will not only solve a cosmic mystery, but will also expand our knowledge of the fundamental forces and particles that shape the universe. Supermassive stars like R13601, found in the dense R136 star cluster in the Large Magellanic Cloud, represent some of the most extreme cosmic phenomena. The formation of such huge stars, which can be hundreds of times the mass of our Sun, requires special and exceptional conditions that are still the subject of intense study and debate among astronomers. Formation begins in giant atomic clouds, large regions of cold gas and dust where stars are born. For a supermassive star to form, a dense region of one of these clouds must collapse under its influence. The key to the birth of a massive star like R136A1 is the accretion of massive material from the surrounding cloud. It can occur in regions where star formation is very active, and the mass and density of the atomic cloud are very high. When the main gas cloud collapses, a protostar forms and rapidly gathers material. In environments such as the R136 star cluster, neighboring stars and intense radiation can stimulate this accretion process, not only fueling the growing protostar, but also helping to remove excess gas that might otherwise limit its growth. Despite these factors, Maintaining stability is challenging because the intense radiation pressure of a supermassive star can counteract gravity and prevent further growth. During evolution, supermassive stars burn their nuclear fuel incredibly fast. Extreme temperatures and pressures are reached in their cores, allowing heavier elements to fuse. However, this accelerated fusion process means that their lifetimes are surprisingly short. Usually only a few million years compared to billions of years for lower-mass stars, such as our Sun. Large stars change at the end of their life cycle. They may explode as supernovae or supernovae, releasing huge amounts of energy and enriching the interstellar medium with heavy matter. Sometimes they leave behind a dense core that falls into a black hole. Because of these events, massive stars play an important role in the flow of matter and the evolution of galaxies. Each stage of their life cycle provides an important account of the extreme conditions and processes that shape the universe. Speed clouds are mysterious. Fast-moving wind clouds moving through the Milky Way galaxy at hundreds of kilometers per second, associated with the rotation of the galaxy. Their origins are varied and complex, suggesting that many sources and processes may have been involved in their formation. The main hypothesis is that some of these high-velocity clouds are remnants of the galactic initial process. According to this phenomenon, supernova explosions in the Milky Way disk eject gas into the atmosphere. It cools down, cools off, and falls back into the airplane. During the return trip, this recycled material could appear as high-velocity clouds, essentially rejuvenating the galaxy with new cooled gas to promote future star formation. Another likely source of high-speed clouds is the interaction between the Milky Way and its satellite galaxies. When smaller galaxies, such as the Magellanic Clouds, orbit around and sometimes pass through the Milky Way halo, their gravitational interactions and tidal forces can strip gas from these satellites. This escaped gas can then manifest itself as high-velocity clouds. Observations suggest that the Magellanic Stream, a long tail of gas coming out of the Magellanic Clouds, may be a significant contributor to these high-velocity phenomena. Alternatively, some high-velocity clouds may be primordial gas left over from the formation of the Milky Way itself. These clouds may be composed of relatively unprocessed primordial material, representing the remnants of the gas reservoir of the early universe deposited in the galaxy halo. Studying these clouds can provide invaluable insights into the conditions of the early universe and the processes of galaxy formation and evolution. Regardless of their origin, high-velocity clouds play a critical role in our understanding of galactic dynamics and the ongoing processes that shape the Milky Way. By observing and analyzing these fast gas clouds, astronomers are uncovering complex layers of our galaxy's history, interactions, and the continuous cycling of matter in the galactic medium. When galaxies collide and merge, these amazing planetary processes occur over millions and billions of years, changing the structure and dynamics of the galaxies they contain. This process begins when galaxies are brought closer together by gravitational attraction. Contrary to popular belief about violent collisions, collisions between individual stars in galaxies are rare because of the vast distances that separate them. These interactions are mainly gravitational forces acting on stars, gas, and dark matter in galaxies. When galaxies converge, time zones are created in the galaxy and change shape. When round arms expand or twist, streams of stars and gas appear in space. During these close encounters, the gas inside the galaxies is forced to collapse, disrupting star formation. Astrologers refer to stars as stellar starbursts, which can produce new stars faster than normal. Eventually, galaxies pass each other, but are also attracted by the force of the universe, colliding and sometimes passing each other. These interactions compensate for their relative kinetic energy and cause them to merge into a larger galaxy. Over time, the various parts mix and age. The initial chaotic motions of the stars flatten and reshape the progenitors. For example, the merger of two spiral galaxies often results in the formation of a spiral galaxy, characterized by moving stars and a more circular shape. Galaxy mergers are a fundamental process in the hierarchical model of cosmic structure formation. They play an important role in forming larger galaxies from smaller ones, a process known as hierarchical clustering. Evidence of past mergers is abundant, with observations of galaxies with unusual shapes, tidal tails, and stellar streams, remnants of past galactic cannibalism. Even our Milky Way participates in this cosmic dance, still in the process of absorbing smaller satellite galaxies such as the Sagittarius dwarf galaxy. Such mergers not only change the shape of galaxies, but also affect the growth and activity of supermassive black holes at their centers. When galaxies merge, an influx of gas can fuel these black holes, leading to the formation of active galactic nuclei that shine brightly as quasars and other luminous objects. Through these dramatic and transformative interactions, galaxy collisions and mergers play a crucial role in the evolution and diversity of the cosmos. Mysterious ripples observed in the Milky Way's disk have intrigued astronomers, revealing much about the dynamic processes that shape our galaxy. These ripples, or oscillations, in the distribution and velocities of stars and gas within the galactic disk hint at past and current perturbations. Many factors may be responsible for these ripples, with some of the leading explanations involving interactions with other galaxies and internal dynamical processes. One well-known hypothesis suggests that the ripples are the result of tidal interactions with nearby companion galaxies, such as the dwarf spheroidal galaxy Sagittarius. As this smaller galaxy orbits and repeatedly passes through the Milky Way's disk, its gravitational influence could cause waves or ripples in the disk's structure. This scenario is reminiscent of a pebble falling into a pond, where the initial disturbance causes concentric waves. Although in the case of galaxies, the interactions are huge and occur on timescales spanning millions of years. Another reason is ancient collisions and mergers with small galaxies or clusters of dark matter. These events can shake the stars and atmosphere of the Milky Way, leaving lasting ripples after the initial impact. These problems continue as the galaxy evolves, revealing the past history of the universe's interactions. And the central part of the Milky Way, known as the center of the galaxy, contributes to these pulses. As the bar rotates, it exerts pressure on the rest of the galaxy, which can cause ripples and spiral patterns in the disk. This internal dynamical effect could perpetuate and amplify existing ripples, contributing to the complex structure we observe. Studies using data from the Gaia Space Observatory have provided invaluable insights into these ripples. Gaia's precise measurements of the positions, distances, and motions of stars in the Milky Way allow astronomers to map and model disk wobbles in unprecedented detail. By understanding the origin and behavior of these pulsations, scientists can gain deeper insights into the past interactions and internal dynamics of the Milky Way, revealing the complex and ongoing processes that drive the evolution of our galaxy. The hypothesis of Planet 9, a potential large invisible planet in the far reaches of our solar system, has generated considerable interest among astronomers. Evidence for its existence comes from the unusual orbits and behavior of some objects around the Kuiper Belt and other Neptunian bodies. These objects move in extremely long and angular orbits that are difficult to explain and affect known planets. Recently, scientists noticed that the trajectories of these spherical objects show a different pattern. In addition to being randomly distributed, Their perigees, the points on their orbits closest to the Sun, appear to be close to each other. The Shepherd recession strongly suggests the presence of an undetectable mass estimated to be 10 times the mass of Earth. If Planet 9 exists, its gravitational influence could explain the appearance and composition of these distant objects over long periods of time. In addition to clusters, the attraction of Planet 9 may explain other anomalies in the solar system. For example, the orbits of some super-Neptunian bodies have orbital slices rising at large angles relative to the plane of the Sun. It is difficult to fix the contours of these objects without reference to another wave perturbation such as Planet 9. There is much more compelling evidence from modeling and simulations. When researchers incorporate the hypothetical Planet 9 into their solar system simulations, the resulting orbital alignments and behavior exactly mirror the observed distributions of distant trans-Neptunian objects. These models strengthen the theory of the gravitational influence of a large distant planet forming the outer part of the solar system. While the evidence remains compelling, it is important to emphasize that Planet 9 has not yet been directly observed. Their vast distance, dimness, and slow motion make them extremely difficult to detect with current telescopes. Work continues, and researchers are using next-generation telescopes and state-of-the-art surveys to scan the sky in search of this elusive object. If the existence of Planet 9 is confirmed, it will turn our understanding of the architecture of the solar system upside down and provide insight into its formation and evolution. The prevailing theory for the formation of the Moon is the giant impact hypothesis, which suggests that the Moon arose from a colossal collision between the early Earth and a Mars-sized protoplanet known as Theia. This cataclysmic event, which occurred over 4 billion years ago, must have thrown a significant amount of debris into orbit around Earth. Over time, this debris piled up under gravitational forces, forming what we now call the Moon. This theory elegantly explains the Moon's composition, which is strikingly similar to Earth's. Analyzing samples of the Moon delivered by the Apollo mission, scientists found that the Moon is mostly composed of silicates, such as the crust and mantle. The composition of oxygen in the light rocks is similar to Earth's. This suggests an origin, suggesting that the composition of the Moon came from the outer layers of the Earth and Theia, which were previously separate. As a result of this collision, a molten disk of superheated silicate vapor and water formed around the Earth. When this disk cooled and compacted, the first Moon appeared. The high temperatures during the impact and subsequent coalescence would have caused volatile elements to evaporate and volatilize, so the Moon is deficient in these elements compared to Earth. In favor of this theory is also the fact that the Moon's core, relative to its size, is much smaller than the Earth's core. During the collision, much of the iron-rich core of Theia probably merged with the core of the Earth, and the ejected material from which the Moon formed consisted mainly of mantle and crust, which explains its iron-poor composition. The giant collision hypothesis not only clarifies the formation and composition of the Moon, but also provides insight into the dynamic and turbulent environment of the early solar system. Understanding this process helps scientists piece together the history of planet formation and the unique history of Earth and its natural satellites. The hexagonal storm at Saturn's North Pole is one of the most spectacular and unique features of the solar system. The large hexagonal jet stream, first observed by the Voyager spacecraft in the early 1980s and later studied in detail by Cassini, has a cross-section of 30,000 kilometers. The accuracy and stability of the Moon attracted the attention of scientists and stimulated extensive research. The basic concept of the formation of the hexagonal pattern is related to hydrogen and the properties of the atmosphere. Saturn has a vast atmosphere composed of hydrogen, helium, and some heavier elements. The hexagon is believed to be formed by the differential rotation and interaction of jet streams in Saturn's polar region. Essentially, the planet's atmosphere is made up of clouds moving at different speeds and in different directions, creating complex flow patterns. In laboratory models, scientists have reproduced similar shapes by rotating fluids at different speeds. For example, when a liquid inside a cylindrical container rotates at different velocities, a polygonal pattern can form under the action of shear forces and resonance waves. Saturn's atmosphere behaves similarly, where the hexagonal shape is the result of the interaction of deep atmospheric jets and velocity differences creating standing wave patterns. Another factor contributing to the stability and shape of the hexagon is the presence of a powerful polar vortex that anchors the hexagonal jet stream in place. This vortex acts as the center point around which the storm system rotates, maintaining a hexagonal structure over time. Unlike Earth's weather systems, which change relatively quickly, Saturn's storm systems can last for decades or even longer, thanks to their homogeneity and lack of solid surfaces to disrupt atmospheric flows. Understanding the hexagonal storm on Saturn provides insight into planetary atmospheres and the dynamics of fluids under extreme conditions. This also helps scientists make comparisons and find underlying principles applicable to atmospheric phenomena in both our solar system and on exoplanets, showing the broad applicability of fluid dynamics theories in different space environments. Venus's retrograde rotation, why it rotates with the other planets in the solar system, is a mystery that still remains a mystery to astronomers. Unlike Earth, Mars, and many other planets that revolve around the north, Venus rotates. The Sun typically rises on Venus in the west and sets in the east. Several theories attempt to explain this unusual rotational behavior. One popular hypothesis is that the impact was huge during the early formation of the solar system. Just as Earth experienced a cataclysmic collision that led to the formation of the Moon, Venus may have experienced a series of massive collisions with large protoplanets or planetesimals. These collisions could have significantly altered its rotational angular momentum, potentially changing the direction of rotation. Another theory suggests that tidal forces from the Sun may have played a role in Venus's rotation. Venus's atmosphere is incredibly dense, and thick clouds saturated with sulfuric acid create significant atmospheric friction. Over billions of years, the combined gravitational interaction with the Sun may have slowed its rotation almost to a complete stop, allowing negligible forces or remaining angular momentum to gradually reverse the direction of rotation. This process is similar to how the Moon's tidal interaction with the Earth slowed its rotation and synchronized it with its orbit. In addition, complex dynamics in Venus's interior and interactions with its dense atmosphere may have contributed to this unusual rotation. Venus's slow rotation rate, it takes about 243 Earth days for one revolution around its axis, means that its atmosphere circulates faster than the planet itself. This atmospheric superrotation can create surface stresses significant enough to affect the direction of the planet's rotation on astronomical timescales. Understanding Venus's retrograde rotation not only sheds light on the history and evolution of our nearest planetary neighbor, but also expands our general knowledge of planet formation and dynamics. Comparing Venus to other celestial bodies helps to chart the variety of planetary processes and scenarios that may be unfolding in our solar system and beyond. What is the reason for the mysterious feathers of Saturn's rings? These mysterious objects have puzzled scientists for years. The result is the radial wings, a group of ghosts that move around Saturn's circular rings. The answer to their formation lies in the interaction between Saturn's magnetic field and the tiny ice particles in the rings. Most of Saturn's rings are composed of ice and rock, with particles ranging from mechanical dust to stone. These clouds are thought to be caused by the electrical charge of small ice particles in the dust. When the particles are hit by ultraviolet radiation from the Sun or energetic particles in Saturn's magnetosphere, they can become electrically charged. Because these particles accumulate static charge, Saturn's strong magnetic field can lift them above the plane of the rings, forcing them to align along magnetic field lines. The blades appear to stretch out in the form of loops that can move at different speeds. In fact, it appears that the dust particles are picked up and moved by invisible magnetic forces. The wings are most visible when Saturn's rings face the Sun during the planetary equinox. The Cassini spacecraft, which orbited Saturn from 2004 to 2017, has provided valuable information and images that will help scientists better understand this phenomenon. Although a complete picture has yet to be compiled, the interaction of light, magnetic fields, and charged particles provides a clear understanding of the complexity and dynamics of Saturn's rings.